All right, my chemistry students, we're going to talk about thermochemistry. And once again, there should be some familiar ground here based on the thermodynamics you've talked about in your other classes. But I'm going to introduce two techniques that I think you're probably not as familiar with, which hopefully should be pretty interesting. So let's get into it here. So just to make sure that we're all on the same page, our standard enthalpy change, the change in enthalpy for a process in which the initial and final substances are in their standard state. So when we see this little superscript 0 right there, that's our symbol for standard. So the standard state of a substance is going to be given at a specified temperature and its pure form at 1 bar. And typically that specified temperature will be 298 K. So oftentimes when we see this delta H with the little 0, we're referring to whatever its pure form is at 1 bar and typically room temperature. So in physical changes, we will put a placeholder right there depending on what the transition is. So that would be the molar enthalpy change that accompanies the change in physical state, and we'll go through some examples. And then, of course, there's chemical changes. And oftentimes we see an R right there, R for reaction, or sometimes you'll even see people write RXN for reaction. So sometimes I'll write RXN just so it's clear that we're talking about the enthalpy change of a chemical reaction. And recall that calculation goes the sum of all of the products. So we look at the standard enthalpy of formation of the products, and we'll talk about that here in a moment, times the number of moles, minus the standard enthalpy of formation of the reactants times number of moles. And those number of moles are coming from our balanced chemical reaction. And also in the case of a complicated chemical reaction, so something with several steps in its mechanism, the standard reaction enthalpy is the sum of all of those values of the individual reaction. Okay. So let's talk about the enthalpy of physical changes. So just our basic phase transitions here, fusion, vaporization, sublimation, just to name a few examples. And I know that those are like impossibly small right there, probably on your screen, but that says fuse for fusion, vape for vaporization, and sub for sublimation. So this is a very cool technique that is used to measure the thermodynamics of phase transitions. It's called the, I wrote very technique, very cool technique. It's called the differential scanning calorimeter, or differential scanning calorimetry, or DSC as it's known in the industry. So this is a very, very cool technique. So the way this works, you've got two chambers, two separate chambers. One of them is a reference material and the other is your sample that you wish to gain information on. There are two thermocouples, or two temperature probes in each chamber. And each chamber is also controlled by these heaters. So a sophisticated computer program will apply energy to the heaters to raise the temperature of both the reference and sample at the same rate. The reference sample is typically a material that is not going to undergo a phase transition or chemical reaction on the same temperatures as the sample. So as the sample is going through, let's say, some phase changes, for example, that's going to change the heat capacity as we'll be learning. So when you arrive at a phase transition, heat is getting dumped into that sample without changing its temperature because that heat is going into fueling the phase transition. And because this computer program is set up in a way to keep these both at the same temperature, if some process is going on in the sample which takes more heat in, so an endothermic process, or releases heat, an exothermic process, the computer is going to get that feedback, and thus either less power or more power is had to be applied to maintain the same temperature. So the results of that are given in what we call a thermogram. And on the y-axis, that's the power applied to the sample. And on the x-axis is the temperature of the two chambers. And so what you can see here is at the baseline, right, that gives us our reference. And now when excess power is having to be given to the sample to maintain that same temperature, we know that there's an endothermic phase transition going on. Okay, so this is just a random example, so we can see here some glass transition is occurring, some phase to a glass-like substance. Now, as we go into a different temperature, you can see now we get this exothermic phase transition. So heat was released, so therefore power had to be taken away, or less power was applied to maintain the same temperature. So now we can see an exothermic phase transition, and then corresponding to crystallization. And now you can see an endothermic phase transition corresponding to melting. And then finally here we would get another exothermic phase transition corresponding to another phase not indicated here on this graph. Okay, so this can also be applied to chemistry. So we can look at how much heat is applied into a chemical reaction. But most notably, this is typically done for physical changes. Okay, so let's talk about chemical changes. So standard enthalpy of formation is our base value in studying thermochemistry. So the standard enthalpy of formation is the reaction enthalpy for the formation of a compound from its elements in their reference state. And reference state we defined above, the most stable state of a substance at 1 bar and typically room temperature, which says right there. Okay. And so we still have the same formula, sum of the products minus the sum of the reactants. But now what we recognize our reaction for our standard enthalpy of formation is how we build up this molecule from its elements in their reference state. So for example, with this methane, if I wanted to look at what that reaction corresponds to for the enthalpy of formation of methane, I start with methane as a product. So then the reactants have to be carbon solid and hydrogen gas, because at 1 bar and room temperature, that will be the reference states for both carbon and hydrogen. And now, of course, we have to balance that. We'd have to put a 2 in front of there to indicate that that is balanced, giving us 4 total hydrogens. And that number, gets supplied into this equation right here. So this, as you can see, for the formation of methane, heat is released to make methane. So methane is more stable than its elements from which it is created. But now if we look at liquid benzene, it has an endothermic enthalpy of formation. So that means the formation of benzene requires an input of energy. Okay. So there's another device that we could use to quantify thermochemistry, and we'll get to use this in PChem lab in Chem 363, and that is the adiabatic bomb calorimeter. So we have the same equation here, sum of the products minus the sum of the reactants. But now specifically in the adiabatic bomb calorimeter, this is used for determining the enthalpy of combustion. So there's a delta C right there. I know it's small, but I'll tell you that C stands for combustion. And just as a reminder, the F stands for formation. So what happens in these bomb calorimeters is you place a sample in this sample cup, which is in a pretty thick-walled steel container that is then placed inside a water bath. Okay? The bomb, this steel container, gets charged up with a large amount of oxygen, so typically about 30 atmospheres of oxygen. And these detonator leads will ignite the sample. And the way that the delta H of this reaction is determined is by carefully monitoring the temperature of this water bath before and after reaction, which will give a temperature rise, right? So you're combusting something, you're exploding something inside this thing. So those are always exothermic, as you can see from the negative signs there. So that releases heat into the water, and doing some calculations, we can work out what the delta H must have been. So the reaction here that we're interested in, so for example, if we go back to that methane example, right, it's our classic combustion reaction to make CO2 and H2O. And of course, we have to balance it, right? So we'll put a 2 in front of there and then another 2 in front of there, assuming I still know how to balance chemical reactions. So what's pretty cool about this, so you can see this is showing some pretty standard compounds, but I'll highlight specifically glucose here. So if you think about it, that glucose reaction, glucose combustion, that is overall, from initial to final, the same reaction going on in human respiration. Obviously, it's very different within the path of that, but from the initial state to the final state, those are one and the same. So the bomb calorimeter is often how we determine caloric content. Caloric content. So you can put food stuff in here and determine how many calories were in that. And we'll get to do that experiment in PChem lab. It's going to be awesome. Okay, I'll see you in the next video.